Okay, so the first video I put on YouTube from Constructor's Corner about the prime numbers and the logarithmic spiral wasn't very descriptive. It was actually confusing and wasn't very good. But it wasn't so much the idea's fault as my explaining ability. And I'm here to show you what I've been working on in a more clear and concise manner. And hopefully you can view it. Hopefully you can see at least some of the text. You should be able to see if I have the right aspect ratio. I don't have the MPEG-4 encoder, so I'm hoping that it recompresses right. Okay, so the first slide you see here is a paragraph, and hopefully you can read it. But if you can't, I'm going to read it for you. Okay, we start with approximate involute. By the way, an involute is a type of logarithmic spiral. Okay, this approximate involute has prime values that occur every pi radians. Okay, we made this involute. We're saying that every pi radians, 90 degrees, we're gonna put a prime value on this circle that's unraveling. It's an involute, and it unravels as it turns. So as the angle increases, the arc length and radius increase at a certain rate. But it isn't a perfect involute. It's kind of approximate because it shifts and it moves with the prime numbers. But that's okay, because we're going to say that we're going to have a logarithmic spiral later on that's going to fit these measurements and fit in the same way that we will tell there's a well, I'm getting ahead of myself here, but okay, from this involute, from the equations, we derive a polynomial equation, which is the parabola. Okay, the parabola is directly derived from this spiral we just used, what I call the involute. It's derived from that. Okay, the parabola was found by substituting two known prime numbers that occur in a series. However, the prime number is true for all values. So if you test this, you're going to say, "Oh, a prime number should look like this." When you plug it into the parabola, it's always going to be true. You're always going to get a value. It's always true. But that's okay, because the prime numbers lie somewhere along here. Here's what makes a parabola useful. However, on the theory that all parabolas can be described by a logarithmic spiral, we use the equation of the logarithmic spiral and take the values of parabola to solve the equation of the logarithmic spiral. Okay, we're going to derive a logarithmic spiral that describes this parabola, because we couldn't find this logarithmic spiral any other way, because we have like a random curve. It just looks random. There's nothing unique about it. This thing, well, other than we put prime numbers every pi radians. But this time we're going to have a logarithmic spiral taken from the parabola, which is going to intersect the same values of the involute. This is an important step. It is important, and the whole thing theory relies on it. Just about we must be sure that we have truly found the logarithmic spiral, which is defined by the parabola. That means we have to is that logarithmic spiral actually part of that parabola? And if not, then we have to find the one that does. And if it is, there should be a distinguishable pattern of prime numbers on the logarithmic spiral that we just found. I know it sounds complicated, but it does get confusing. You can be adding this thing and looking at this thing and trying to evaluate the values, and it's confusing. But there's one thing: you're going to get this parabola, and you're going to wonder, hey, this parabola just looks ordinary. Yes, it does look ordinary, but that's because the values from the you just don't take 19 and 33 and 13. You just don't take 19 and 23 from the parabola. You have to put them in there so that p2 squared divided by pi squared is like you'd square 19 and divide it by pi squared, and you would square 23 and divide it by pi squared. Then you might see a pattern. And also, another reason with the parabola that it's shifted I'm using relative values from its origin. But if I have to move that origin to 0, 0 to make the calculations easier. Okay, and now for this inspection of this parabola, how are we going to get a logarithmic spiral? So we make some inspections that s is equal to f at x, r is equal to the summation of x, and pi is equal to s over r, and we're filling these values. We're looking to get the derivative of r as compared to derivative theta, so we can plug it into the logarithmic spiral equation. That equation is here it is, derivative of r over the, as opposed to the derivative of theta is equal to a times b times e to the b theta is also equal to br. And this equation, I often wondered if I knew more about how this equation was formed, if I could find something better, because finding the derivative of r as opposed to theta it's a lot of runaround, and I'm not even sure that's correct, but it's part of the idea. I just want to show this. If this idea works, that's great. If it doesn't, it's a concept that it's working towards something. It's complex, I know, but it might not work because I'm putting in values and placing the way it's set up. But if it did work, there's something there, you know. If you could, even if it fails, I believe that the concept is still good about putting in information to a logarithmic spiral, finding a logarithmic spiral from a parabola. It would work on encryption. It works on finding series. There's something there. It just seems too unbelievable to work. It seems like it was. This is prime numbers is a 3,000 euro problem. You're not going to solve them overnight, but this might be like a step along the way. It's not complete. I know not. I've plugged in the numbers and I'm still not sure of what I'm getting, but I just want to show you the concept. It's all about the concept. And once you have dr as to d theta, which you're looking for, you just substitute it in, and then you find b and a in the logarithmic spiral equation. You find b and a, and that would give you the logarithmic spiral. Let you judge and see what you think. Send me feedback. My email is truel_the_constructor@hotmail.com. It's on my website, www.constructorscorner.com.